Yay, it says I'm live, finally. Goodness gracious. My apologies to those who have been waiting. Having a little computer issues, but here we are. So right now, for those of you on the computer, you're seeing an email that I got about SAT, PSAT. Obviously, now here's the thing. I have no idea what they're doing for virtual kids. Like, if you're fully virtual, are you required to show up? I have no clue. That's a fun fact. But yeah, 9th and 10th graders, regardless of their group. Now, the thing is, 10th graders typically also take the PSAT, but they're not taking it tomorrow. Instead, there it is. For planning purposes, October 29th will be a similar type of day. That'll be a Thursday where all sophomores will take the PSAT and everyone else will be on a read day. So look forward for that for the 29th. That's you guys sophomores. Yeah, so there you are. Yeah. So it's gonna be a fun time all around tomorrow. I don't know. It's basically gonna be an extra day off for some people, but it's an extra day in school for some people. Yay! So, happy day. Here we are again. So let me get this loaded up. Then let me tell you guys what's gonna happen. First and foremost, I do have a video to kind of start this introduction for today to kind of get you where we're going, and we'll get it started in a minute. A couple of reminders. On Friday, obviously, you had that Edge Elastic Major due. Make sure you have gotten that thing done. It is late at this point. The project is also due last Friday. I'm beginning to work my way through them slowly but surely. It's going to take me a little bit longer as opposed to other assignments to kind of go through them. But I will give you appropriate feedback when the time's there. There is a quizzes live right now for you. It is a check to see where everyone is at in regards to quadratics. I require that to be done. It is due by Friday. Make sure that you have jumped on that. You do have 3 attempts to get that done, so make sure that you do, and everything is fine and dandy. And we'll kind of go from there. Now, as for today, last week, we did a deep dive into the quadratic formula. Negative b plus or minus square root b squared minus 4ac all over 2a. And actually, let me switch over to Desmos real quick so you can see what I'm referring to. Click, 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 Desmos. Eventually, I'm going to get into the details of this, where you have a quadratic that looks like that. And last week, we talked about finding the solutions of said quadratic. And for this one in particular, it would have no real solution. It would have no real solution. The reason why, it does not cross the x-axis. If it does not cross the x-axis, then it has no x-intercept and it doesn't have any real solutions. And I kept emphasizing, for now, it doesn't have any solutions. For now, we can't do anything about it. For now, don't worry about it. But now we are. Now we are going to worry about it. See, a long time ago, you guys learned about basic numbers, like what, 1, 2, 3, 4, 5, stuff like that. You may not know what to categorize them as, but typically those are called the counting numbers or the natural numbers or something like that. Typically when kids are counting, they usually start with like a 1, 2, 3, junk like that, and they start counting on their fingers, which is great. I tell you about my son and his math. I tell you about that? It's fantastic. My son is learning how to add numbers together where they get 2-digit answers. 2-digit answers. He's in 1st grade. And he's sitting at the table the other night, and he's trying to figure out 8 plus 7. And he's counting on his hand, and he obviously goes past the number of fingers that he has. And he's trying to figure out 8 plus 7, and he's asking me for help. And I'm trying to kind of gently kind of roll him into it and things like that. And then he stops me, and he says, wait a minute, I got it. And he wrote down 15. And I said, great job. How did you get that? How did you know 8 plus 7 was 15? And he said, well, I saw 7 plus 7 was 14. And I figured that 8 was 1 more than 7. And I thought, what an amazing 1st grader. Fun fact, he hates math. Go figure. Anyway, back to this. After natural numbers, You guys learned about numbers that they called it a bad name. What are the numbers on the other side of the number line? What are the numbers to the left of 0? Yeah, they're bad numbers. We called them negative after how we felt about them. What a terrible name. But then we discovered numbers that were a little bit better. We discovered fractions, and we called them rational. We called them rational numbers. What's the root word of rational? Root word of rational. First 5 letters of rational. Ratio. We called them ratios. 1 to 2, 2 to 3, 3 to 4. We called them ratios. Rational. It's a pretty nice word to call them. But then we discovered numbers that could not be written as rational numbers. They couldn't be written as rational numbers. And we called them irrational. There's your square root of 2's and your pi's and things of that nature. So like here's like 1, 2, and 3 existing in their own little bubble. And then we discovered negative numbers existing in their bubble. And then we discovered fractions existing in their bubble. See, the thing is with these natural numbers and these integers and these rational numbers, see, the thing is everything inside the bubble can be considered, like, for example, rational. Like 3 is a rational number, 3 over 1. Negative 2 is a rational number, negative 2 over 1. All of these are rational. Then we discovered what we call the real numbers, which now include pi and the square root of 2. All the numbers within this bubble would be considered real. But then we discovered numbers that don't exist in any of these bubbles. They exist outside of this bubble. They exist in another plane of dimension. And they are known as the complex numbers. I have a short video that I want to show you in regards to that. So let's see what it has to say. Click, click, click.
Let's say we're given the function f of x is equal to x squared plus 1. We can graph our function and get a nice parabola. Now, let's say we want to figure out where the equation equals 0. We want to find the roots. On our plot, this should be where the function crosses the x-axis. As we can see, our parabola actually never crosses the x-axis. So according to our plot, there are no solutions to the equation x squared plus 1 is equal to 0. But there's a small problem. A little over 200 years ago, a smart guy named Gauss proved that every polynomial equation of degree n has exactly n roots. Our polynomial has a highest power or degree of 2, so we should have 2 roots. And Gauss's discovery is not just some random rule. Today we call it the fundamental theorem of algebra. So our plot seems to disagree with something so important, it's called the fundamental theorem of algebra, which might be a problem. What Gauss is telling us here is that there are 2 perfectly good values of x that we could plug into our function and get 0 out. Where could these 2 missing roots be? The short answer here is that we don't have enough numbers. We typically think of numbers existing on a one-dimensional continuum, the number line. All our friends are here. 0, 1, negative numbers, fractions, and even irrational numbers like root 2 show up. But this system is incomplete. And our missing numbers are not just further left or right, they live in a whole new dimension. Algebraically, this new dimension has everything to do with a problem that was considered impossible for over 2,000 years, the square root of negative 1. When we include this missing dimension in our analysis, our parabola gets way more interesting. Now that our input numbers are in their full 2-dimensional form, we can see how our function x squared plus 1 really behaves. Our function does cross the x-axis. We were just looking in the wrong dimension. So why is this extra dimension that numbers possess not common knowledge? Part of the reason is that it has been given a terrible, terrible name. A name that suggests that these numbers aren't even real. In fact, Gauss himself had something to say about this naming convention.
I'm just going to skip this part because he just is quiet for like 5 seconds. He thinks that you're going to read all that.
So yes, our missing dimension is comprised of numbers that have been given the ridiculous name imaginary. Gauss proposed these numbers should instead be given the name lateral. So from here on, let's let lateral mean imaginary.
Also, I'm not going to call them lateral. Lateral's a dumb name. I'm going to call them by what they actually are called. They are called complex numbers.
To get a better handle on imaginary, I mean lateral numbers, and really understand what's going on here, let's spend a little more time thinking about numbers themselves. Early humans really only had use for the natural numbers, that is 1, 2, 3, and so on. This makes sense because of how numbers were used. So to early humans, the number line would have just been a series of dots. As civilizations advanced, people needed answers to more sophisticated math questions, like when to plant seeds, how to divide land, and how to keep track of financial transactions. The natural numbers just weren't cutting it anymore, so the Egyptians innovated and developed a new high-tech solution: fractions. Fractions filled the gaps in our number line and were basically cutting-edge technology for a couple thousand years. The next big innovations to hit the number line were the numbers 0 and negative numbers, but it took some time to get everyone on board. Since it's not obvious what these numbers mean or how they fit into the real world, 0 and negative numbers were met with skepticism and largely avoided or ignored. Some cultures were more suspicious than others, depending largely on how people viewed the connection between mathematics and reality. And this is not all ancient history. Just a few centuries ago, mathematicians would intentionally move terms around to avoid having negatives show up in their equations. Suspicion of 0 and negative numbers did eventually fade, partially because negatives are useful for expressing concepts like debt, but mostly just because negatives kept sneaking into mathematics. It turns out there's a whole lot of math you just can't do if you don't allow negative numbers to play. Without negatives, simple algebra problems like x plus 3 equals 2 have no answer. Before negatives were accepted, this problem would have had no solution, just like we thought our original problem had no solution. The thing is, it's not crazy or weird to think these problems have no solutions. In words, this algebra problem basically says, if I have 2 things and I take away 3, how many things do I have left? It's not surprising that most people who have lived on our planet would be suspicious of questions like this. These problems don't make much sense. Even the brilliant mathematicians of the 18th century, such as Euler, didn't really know what to do with negatives. He at one point wrote that negatives were greater than infinity. So it's fair to say that negative and imaginary numbers raise lots of very good, very valid questions. Like, why do we require students to understand and work with numbers that eluded the greatest mathematical minds for thousands of years? Why did we even come to accept negative and imaginary numbers in the first place when they don't really seem to be connected to anything in the real world? And how do these extra numbers help us explain the missing solutions to our problem? Next time, we'll begin to address these questions.
There won't be a next time. The next time he goes into like way deeper things than we would ever get into in Algebra 2, but that is okay. The point is this. If I go to my son and I say, you're holding 2 apples and I'm going to take away 3 apples, he has no idea how to answer because he has no concept of negative numbers. You are at a point in high school where negative numbers and 0 and things like that, you use them in mathematics all the time. You've come to accept the fact that they exist and you're somewhat comfortable with negative numbers and 0. But there is a concept of numbers known as complex numbers, which don't really have a tangible, real world, hold in your hand type of situation, but they do exist and they do apply to things. In fact, you won't really have a real world application for complex numbers unless you decided that you were going to go to college for some advanced engineering degree. If you did, then you would see the real life applications of complex numbers. But as for now, I have to take baby steps. We got to introduce you to the concept. So, ladies and gentlemen, if you would, I'm going to need those notebooks out and open. Let's see here. Get away. Come back. You go there. And you go there. And okay. And down. Let's see what we got here. Here we go. So this is going to be called quad formula continued. just abbreviating, today is the 13th. Quad formula continued, parentheses, complex numbers. Over here, there we go. The square root of -1. Now, last week, I asked you guys various questions about square roots. And I said something like, okay, what's the square root of 81? What would you say? What's the square root of 81? Why? That's how you would check them, right? Square root of 81 is 9 because 9 times 9 is 81. You could say the same thing for the square root of 144. You guys know square root of 144 off the top of your head? 12, because 12 times 12 is 144. You guys know the square root of 441 off the top of your head? Ah, close. Think about it. If it's 22, 2 times 2 is 4. It's 21. Yeah, you're close, though. That was a good guess, though. Because 21 times 21. Now, square root of -1. We can't say the answer is 1 because 1 times 1 is 1. We can't say the answer is -1 because -1 times -1 is also +1. Doesn't work. There is no number that exists in the real numbers that answers this question. But mathematicians kept coming up to this number known as the square root of -1. In fact, if you went to your graphing calculators, which don't worry about that right now, just focus on what I'm going to show you. But if you went to your graphing calculators and you attempted to say, okay, graphing calculator, tell me what the answer is to the square root of -1, it gives you an error. But look at what type of error it gives you. Look at what type of error it gives you. Non-real answer. Again, the real numbers are everything in those bubbles that I showed you earlier. Pi, the square root of 2, the fraction 3/4, -5. Things like that are considered the real numbers, which is why people have referred to this as a imaginary number. Imaginary is a terrible word because they exist. They exist and they have real world consequences. So there is a way to change your calculator. I don't know if you knew you could do this. Some of you do. If you've ever been to mode, you can change the mode on your calculator and change it from the real number system to the complex number system. And by doing that, you're basically telling your calculator, stop telling me it's a non-real answer. Stop telling me it's an error and actually give me the calculation, which it does. It gives you that calculation. For now, forevermore, let it be known that if you ever have to do a calculation of the square root of -1, you are referred to it as I. I also led to people calling them imaginary numbers, but unfortunately, stop calling them that. I don't know. Just they're complex numbers. They're complex numbers. This is a complex number. Mathematicians tend to name things after how they feel about them. So we give like bad names or negative names or irrational names to things that we don't understand and don't like. So we called them imaginary or complex because they were difficult or hard. Check this out. On your graphing calculators, and even the ones that you have on your computers, look what's written above the decimal point. I. It's been staring you in the face this whole time. It's been there this whole time. Just sitting, mocking you ever so gently. But that's what that thing does. It's fantastic, really. Let me give you an example. So, for example, if I wanted to evaluate the square root of -9, well, I know what the square root of 9 is. I know that the square root of 9 is supposed to give me 3. But what about the square root of negative 9? Here's what you can do. Y'all remember when you did Pythagorean theorem and you had to like simplify radicals and your teacher wouldn't allow you to get like the decimal? Yeah. Remember how terrible that was? Yeah. You have to do the same thing here. You can break this thing apart to be the square root of 9 times the square root of negative 1, because you can split them like that, multiplied together. And then you know that the square root of 9 will give you 3, and the square root of negative 1 will give you I. Forevermore, the square root of negative 9 will be a 3I. And if you set the mode on your calculator will tell you the exact same thing. Square root of negative 9. Beat 3I. That's what it does. It's very weird. It's very strange. But that's what it does. Let me give you an example here. Now, just something as a side note. I squared. Now, I squared is taking a complex number, I, and multiplying it by itself, I. Let me show you what the calculator says, and then let's actually figure out why that is. I squared. This is going to come into play eventually. So if I have I squared, look what the calculator says. Shabam! Negative 1. Why is that? That's a big question. It's a big question. It's not easily answered, but it's a big question. Why in the world did I squared get you negative 1? We'll check this junk out. I squared is really this squared. Because, as we said, I is the square root of negative 1. And I can replace or substitute this I for the square root of negative 1. What, pray tell, happens if you were to take a square root and a square and they come into contact with each other? What happens if a square and a square root come into contact with each other? Ooh. What happens when addition and subtraction come into contact with each other? They do. Same thing with multiplication, division. Same thing with square roots and squares. They cancel each other out. And if they cancel each other out, you are left with negative 1, which is no longer a complex number. It's a real number. Very strange. It's like, imagine I take a ghost and I multiply it by a ghost and I get a living human being. It sounds ridiculous. But I'm taking well, for the lack of a better term, the term that I don't like, imaginary. I'm taking an imaginary number and multiplying it by an imaginary number, and I get a real number. I have a magnet on my fridge. Let me see if I can find it. Hopefully it'll show up here. There it is. I have a magnet on my fridge that says this. And I thought it was funny. So it's a magnet on my fridge for the past 12 years. Nobody gets me. I laugh at it every time. I guffaw at it. Anyway, back to this. Now let me change this to just +1. There we go. See this thing right here? I can't bring that down to the x-axis. I can't get a solution out of it. But according to Gauss, that thing should have 2 solutions. 2 solutions. Last week, I told you that there were only 3 things we could possibly do. We could get 2 real solutions, 1 real solution, or no real solutions for now. this thing would have no real solutions. But it would have two complex solutions. And that is what we're about to find. So, flip, expand, new page. Let's try to solve the following. Example. Solve. I'm going to choose a different one. X squared plus 9 equals 0. And I would say, hey, let's solve this thing. Let's solve it. Okay, x squared plus 9 equals 0. Let's solve you. All right, let's go to the method that I like better. I like the Tucker method personally, but let's just do a factoring thing here. Okay, what's my b value? If I'm trying to solve this thing by factoring, what's my b value? Yeah. Can you think of two numbers that multiply to 9 but add up to 0? 3 times 3 would give you 9, but 3 plus 3 would give you 6. But they don't multiply to positive 9. Yeah. 3 and negative 3 can't work because they got to multiply to positive 9. 3 and 3 can't work because they have to add up to 0. Negative 3 and negative 3 can't work because they got to add up to 0. I guess we can't factor this. So, based on what we did last week, if you can't factor it, then you have no choice. We have to go to the quadratic formula. So let's write it down. Let's remind ourselves as to what it is. Reminding ourselves of the quadratic formula, you got a negative b plus or minus square root b squared minus 4ac. You guys remember what that was called, the b squared minus 4ac? It had a special name, discriminant. Just rolls off the tongue. And the whole thing was over 2 times a. Let's identify a, b, and c. A, b, and c. I know that b is 0. We just said that. A was 1, and c was 9. All right. Let's calculate a discriminant. B squared minus 4ac gets you 0 squared minus 4 times 1 times 9. Let me zoom in a little bit on that. There we go. Ugh. Oh, wait, that's not too bad. It gets you a negative 36. But it is negative. It is negative. That's weird. Okay, let me make a note for myself here. Because discriminant is negative, no real solutions. Because the discriminant is negative, there are no real solutions, and notice that I capitalized the word real. Because there are solutions to this problem. There is a solution to this problem, but there's no real solution to this problem. So let me make another note right here, all caps. However, there are 2 complex solutions. There are 2 complex solutions. Let's find them. I'm going to use the rest of the quadratic formula where it goes negative b plus or minus the square root of the discriminant. The whole thing is over 2 times a. Let's simplify that junk down. Negative 0 is just 0. And if you add 0 or subtract 0, it doesn't do anything. So screw that 0. Since I'm saying screw that 0, it's really this. It's really plus or minus. I'm going to break this thing apart. Square root of 36, square root of negative 1. Because I know what the square root of 36 is. It's 6. And I know what the square root of negative 1 is. It's I. The whole thing is over 2. This becomes the plus or minus 6i over 2, which just simplifies to become plus or minus 3i. I don't know why I've always done this. I've done it for T's, but I'm also doing it for I's. I always put like a cute little tail on the end of the I. It just makes me feel warm on the inside. I hope it makes you feel warm too. Anyway. How do I make sure I'm right? How do I know I'm right? How do I know that I've actually gotten the correct answer? This is strange. This is strange. Ooh. How do you normally check to see if you're right? I don't know what you mean. What do you mean use the calculator? Because here's the thing. I could, quote unquote, use the calculator to look at the graph. But the problem is if I looked at the graph of x squared plus 9, this thing does not cross the x-axis. I can't just do trace 3i because it won't work. It won't work. What do I do? Let's zoom back out. See, normally, if I gave you an answer, like, I don't know, if I said, hey, x plus 1 equals 7, and then you got x equals 6, how do I check to make sure I'm right? How do you know that 6 is the answer? This is going back to like, I don't even know what grade, pre-algebra. Weren't you always taught plug that sucker back in? Plug it back in. Make sure that it works. Let's do it. Let's plug it back in and see if it works. I got 2 answers. 2 answers. I got an answer of positive 3i and negative 3i. Let's see if that works. Let's plug in the 3i and see what happens. If I plug in 3i right there, if I'm right, the result should give me 0. What? 3i squared is really 3i times 3i. 3 times 3 gives me 9. What's I times I? What's I squared? Negative 1. Really gives me a negative 9. So this is really negative 9 plus 9. Holy crap, it works. Holy crap, it works. Check this trick out. This is really messed up. You have always been taught. What happens when you square a negative number? What happens when you square a negative number? It becomes positive. There's the negative number right there. There's 2 negatives right there. Negative times a negative. Positive. Yes, positive. However, I times I gives you negative. Negative 9. It still works. It's really messed up. It's really messed up, but it works. Mathematics is the only subject on this planet that is perfect. It works. Even if we don't understand it, even if we don't have a way of actually describing what is happening, rest assured that mathematics is the only subject that is absolutely 100% perfect. Mr. Murky, math is not perfect. No. Human beings are not perfect. Human beings are not perfect. Math is perfect. Let's go back to this. Click. This is an example that I gave you last week, and I want to do this example with you. The example is x squared plus x plus 1. No real solutions. Yeah. I know it's no real solutions. We're going to find the two complex solutions. X squared plus x plus 1 equals 0. A, B, C. This is what we did last week. Last week, I gave you a problem. I had you identify A, B, and C to get the discriminant. You plugged junk in, and you were able to give me a final answer. This is what we did last week. This is why I said this is quadratic formula continued. Let's see what happens. B squared minus 4AC gives you a 1 squared minus 4 times 1 times 1. Lots of ones floating around. Holy crap, this gives me a negative 3? That's terrible. Yes, it is. It is terrible. Last week, you would have written no real solution and be done. This week, you have to go farther. This week, you have to go farther. Check this junk out. Negative B plus or minus the square root of the discriminant. The whole thing is over 2 times A. Oh, crap. There's a negative in a square root. Check this out. I'm going to write something down, and it's going to mess with your heads. Look what I just did. Look what I just did. Write that down. It's going to mess with your heads. Write that down. What I just circled was the answer. That's all you have to do. If you can simplify it farther, you should. If you can simplify it down farther. But there's going to come a time where you can't simplify it down anymore. The negative b just gave you a negative 1. I can't do anything there. The 2 times 1 just gave you a 2. Okay, fine and dandy. I got the square root of negative 3. See, the square root of negative 3 can be broken up like this. The square root of negative 3 can be broken up to be the square root of 3 and the square root of negative 1. According to what you did last year in geometry, you can't simplify the square root of 3 any farther. The square root of 3 is like 1.73 and change. You can't simplify that. You can't do anything to it. But the square root of negative 1 is an I. That's all you can do. So here's your shortcut. Here's an amazing shortcut. Plug that in. There we go. If you ever have a negative under a square root, you can remove that negative and make it become an I. It's not that the negative itself is I. It's that that negative was underneath the square root. And the square root of negative 1 just becomes that I. Typically, we were at the I before the square root. It's a logistical thing. But that's all you got to do. Check out this junk. I'm going to check my answer. I'm legitimately going to check my answer. It's going to be messed up. Check this out. If I'm correct, that if I take negative 1 plus I, the square root of 3, divided by 2 squared plus parentheses, parentheses, negative 1 plus I, the square root of 3, close, close, divided by 2, boom, plus 1. What I just did was check this out. Here is x squared plus x plus 1. If I'm correct, what should happen when I hit enter? Because remember, this was x squared plus x plus 1 equals 0. If I'm correct, what should happen when I hit enter? What should the whole thing equal? Somebody's whispering it. 0. Yes, of course it is. Yeah, it should equal 0. If I'm correct, this whole thing should equal 0. Chapow, of course I'm correct. Never have a doubt. Of course I'm correct. Oh, it's really messed up. You want to see something? I'm going to take a little rabbit trail right now. You want to see something really messed up? Okay, watch this. I'm going to show you. This is a complete side note right here. Check this out. I'm going to show you a number on the calculator called E. E is equal to 2.718 and change. You guys are familiar with pi. You know, pi 3.14159265535, that number, of course. 3.141, ... And of course, you know, I is equal to the square root of -1. Look at these three numbers. Look at these three numbers. They're terrible numbers. They're terrible, horrific numbers. But I'm going to show you something. I'm going to take that number E, I'm going to take that 2.718 number, and I'm going to raise it to the power of the square root of -1 times 3.141, blah, 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 blah. I'm going to raise it to the power, caret symbol. Look at this. This is one of the greatest calculations in the history of mathematics. First and foremost, there's E. There's pi. And of course, you already know I. All three of those. Check out this junk. One of the greatest calculations in the history of mathematics. Chapow. It's amazing. It's beautiful and it's wonderful. And it's scary all at the same time. That something like that exists. Anyway, back to this. Here's what I need from you. Last week, I gave you a worksheet. I don't know where my extras are at the moment. I should have a couple extras floating around here. But that worksheet should have said 4.6 practice. For those of you in the live stream right now, this PDF file of practice 4.6, this is what it looks like for those of you in the live stream. This practice should be in a PDF form on the stream in Google Classroom. I believe I moved it close to the top. The PDF you can just click on and it just pops right open. It's fantastic. I want to knock out some problems from here. Anybody need a copy? Because I got plenty of copies. Okay. First and foremost, we're going to do number 26. We're going to do number 26 together. So please write down number 26. If you need, oh, you got it. There it is. Just making sure. Write down number 26. Now, if you notice for problems like number 26, they're asking you to do a few things. They're asking for you to find the value of the discriminant. And then based on the value of the discriminant, they want you to say how many solutions and what type of solution are you going to get. And then from there, they want to know the exact solutions by the quadratic formula. That is exactly what we're going to do with number 26. So this is example number 26. This is x squared plus 3x plus 6 equals 0. Fantastic. So this is the exact process that we went through last week. A equals, B equals, C equals. 1, 3, 6. Very straightforward. B squared minus 4AC, they want the value of the discriminant. Oh, crap, that's like 9 minus 24. 9 minus 24 is negative 15. Ugh. Negative 15 for my discriminant. According to the notes from last week, and I'm answering the question on the worksheet, that's no real solutions. Correct. But it also means two complex solutions. There's the value of the discriminant, and there are the number and type of solutions. But now they still want to know what is my exact answer. And with my exact answer, I would still follow the quadratic formula. Negative b plus or minus the square root of the discriminant, the whole thing, over 2 times 1. Now I got to simplify some junk up. Let's simplify it like this. Well, that negative of 3 is just negative 3. The bottom of the fraction is just a 2. But look what I'm about to do with the square root of negative 15. Now, the square root of 15, can you simplify the square root of 15? No. But you can take that negative as a negative 1 that is underneath the square root. It's a square root of negative 1. I can just write it like that. Done. That's all you have to worry about. That's all you have to worry about. It's phenomenal. It really is phenomenal. Here's what I want you to do. Pick a number from 15 to 29. Pick any number from 15 to 29, but you can't pick 26 because we already did it. Pick a number. No guesses? Sure. Pick one. But it can't be 26. Sure, let's do 28. Here's the thing. It doesn't matter which one we choose. Because now you have all the tools that you need to get this thing done. You have all the tools that you need to get this thing done. All of it. It's phenomenal. That's what we're going to do. So he says he wants to take a look at number 28. Sure. Let's take a look at number 28. 28. Yeah. Why is this paper bending on me? 16x squared minus 8x plus 1 equals 0. I think I know where this one's going. Now, obviously, maybe I would try 2-factor first, but I'm not going to bother with that because this problem wants the quad formula. So let's do the discriminant. Save some space here. B squared minus 4ac is negative 8 squared minus 4 times 16 times 1. Now, this is very interesting. This is very interesting. Let me show you something in the calculator. This is very interesting. If I did this calculation, parentheses will save your life. Boom. It just gets you a 0. According to our notes from last week, what does a discriminant of 0 tell you about the solutions? One real solution. Now, that still complies. Remember the video we watched at the beginning of class where it says like the degree says that's how many solutions you should get? You're telling me one. It really should be 2 solutions. In reality, it's a repeated solution. So it repeats twice. You'd get the same answer twice. So there's still technically 2 solutions. You can't see it right now on the live stream, but I'm making finger quotes as I make that thing. I don't know. Is it obvious when I say it like that I'm making finger quotes? I'm making finger quotes, right? If I say it like that, it's whatever. Shut up. Anyway, back to this. This should be one real solution. Huzzah. All right, let's try it. Negative b. Notice how I wrote negative b. Plus or minus the square root of 0, which in this case, again, we know the square root of 0 is 0. The whole thing divided by 2 times a, which is 16 in this case. That really becomes 8 plus or minus 0, which again, that 0 doesn't do anything, so I'm not going to write it. Divided by 32, which if you know how to do these correctly, you get an answer of 1/4. Oh, happy day. That's what these things do. It's phenomenal. It truly is phenomenal. I got 2 more problems I want to do. Write down number 16. Write down number 16. Let's do it. Number 16. Oh, Mr. Murray, I don't like number 16. I know. That's why I chose it. Mess with your heads. Let's do number 16 together. X squared equals 3x. There's 100 different things you can do here. But tell me, if I'm going to use the quad formula, what do I got to do first? You have to. You have to get it equal to 0. Absolutely, yes, you do. So I'm going to subtract that 3x over. Let's identify A, B, and C real quick. A is 1. B is -3. What's my C value? What's my C value here? Oh, yes, it is. It is indeed 0 here. Be very careful with how you calculate this thing. You got to make sure that you have the correct numbers in the correct location in order to figure out that your discriminant should be a positive 9. And then you would go throughout this process. You got to make sure it's equal to 0. You got to correctly identify A, B, and C. And you got to throw this stuff in where it belongs. In this case, it would be -b. Notice how I wrote it. Plus or minus the square root of 9. The whole thing over 2 times 1. Well, that should be +3. Plus or minus 3. The whole thing over 2. I can take this farther. You're going to have to realize that there are 2 different things you can do here. You can do it once with the addition and once with the subtraction. 3 plus 3 would give me 6. And 3 minus 3 would give me 0. Yay, I got my 2 answers. Let me show you something here. Let me show you something here. Let's go back to this real quick. Let's say, I gotta speak to the microphone. Hold on. I'm gonna speak into the microphone for this. Make my serious voice. Let's say that you went back to the beginning of the problem and the directions said solve. But the directions did not say how to solve. Now, in this problem for number 16, they told you how to solve it. They wanted you to use the quadratic formula, which we did. You can see that on the board. But if you are given the choice, you should always try to factor first. Remind me, what is the first step of the Tucker method? What is the first step of the Tucker method? Greatest common factor. What's the greatest common factor here? It's an x. Yes, it is. You can take an x out. There's no c value. The c value is 0. It's not there. So they both have an x in common. Now keep in mind, this is if they give you a choice. This problem, they didn't give you a choice. They said do the quadratic formula. This one, what if I did give you the choice? You want to take out a GCF? Absolutely. I'll take out a GCF of x, and you're left with this. Now, technically, there's no more quadratic. The Tucker method's done. You can't do a times c because there is no a value to speak of. So technically, this is factored. And since this is factored, and it's multiplying equal to 0, you can take its individual components, and you can set them equal to 0, and you can get your 2 solutions. Now, this is a rhetorical question. Rhetorical question, meaning I don't want an answer. I just want you to think. Just think about it for a second. If you were given the choice between doing this quadratic formula and getting your 2 answers, or this. Personally, I'd probably choose this. But you have to recognize how to do it. I put a star into your notes last week. Last week, which basically said, if you can't factor, the quadratic formula will always work. If you can factor, go for it. But if you can't factor, or if you don't know how to factor it, the quadratic formula will always work. Just something to keep in mind. One more problem, and then I'm done. You know where I'm going on the worksheet. Where am I going? What? No, not 29. I'm going to the word problems. Let's look at number 30. Last problem of the day. You remember when the power went out yesterday? You know what happened? The clocks didn't reset yesterday. They did everything except reset the clocks, but I didn't know that yesterday. I didn't know that they had not reset the clocks. As a result, I thought I had 3 minutes left yesterday, and the bell rang. I'm like, what the crap? They forgot to reset the clocks. You would think, okay, we got the internet back on, we got this back on, blah, 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 blah. You don't think the teachers are keeping an eye on the clock to make sure, whatever. I'm not bitter. You sure sound it, Mr. Markey. Shut up. Let's look at number 30. The height, h of t, in feet of an object t seconds after it's propelled straight up from the ground with initial velocity of 60 feet per second is modeled by the following equation. H of t equals negative 16t squared plus 60t. Oh, the reason why I tell you that story is because I'm actually going to be making a short video going into more detail about this problem, much more detail about this problem, but the video is not for you. The video was for my class yesterday. So just giving you the heads up on that. The question then becomes, at what times will the object be at a height of 56 feet? Let me write something down, and then I'm going to draw a picture on the board. Draw a picture. I like pictures. There are two scenarios that we have here. This object is being propelled up into the air, and then that object is coming down. There are technically two different scenarios, actually three different scenarios for this situation. I'm going to erase these, so don't worry about it. I'm going to erase all of these. You don't have to draw these. I just want to visualize what the heck's going on here. There's actually three different scenarios, and I'm going to go into these details in the video. But this object is being propelled upwards and then downwards, meaning it crosses the 56 feet barrier going up, and then it crosses the 56 feet barrier going down. The second scenario is if the object just hits 56 feet right at its apex and then comes straight down. And then the last scenario is if the object never reaches 56 feet. This is a scenario with two real solutions. This is a scenario with one real solution. And this is a scenario with no real solution. In scenarios like this, they would not expect you to get the complex solution, the imaginary solution, the I solution. They wouldn't expect that simply because it's not realistic in this case. So most likely we have one of these. In fact, it's probably this, but let's just see what happens. Because I have no idea what's going on with this problem. They want to know, according to that formula, when will the object reach 56 feet? As always, I'm going to get one side of my equation equal to 0. As always, I'm going to get one side of my equation equal to 0. Now, if you notice, I moved the negative 16t squared by adding it to each side, and I moved the 60t by subtracting it from each side, because I like having my a value positive. It makes my life better, makes my life easier. Now, yes, you could try the Tucker method, but that's not what I want to do. This whole worksheet's about the quadratic formula. So let's do that. Quadratic formula. B squared minus 4ac is negative 60 squared minus 4 times 16 times 56. Not expecting anyone to do that in their heads, so I'm going to go to the calculator for that. Negative 60 squared minus 4 times 16 times 56. Oh, that's not too bad. Look at that. It gets you a 16. That's kind of nice. That's at least a little bit better. All right, let's plug that junk in. Negative b plus or minus the square root of 16. The whole thing is over 2 times 16. This just becomes 60 plus or minus 4 over 32. And you would have to get me both answers. One answer is if you do 60 plus 4 over 32 and 60 minus 4 over 32. If you did the first one, you would get an answer of 2. If you did the second one, you'd get an answer of 1.75. I go back to the question. The question says, at what times will the object be at a height of 56 feet? I pick both answers. And because that's what this object does, it hits 56 feet going up. It hits 56 feet going down. First at 1.75 seconds and then next at 2 seconds. That's just what this object does. That's what this formula allows you to do. You have to know how to handle the formula. Get one side of the equation equal to 0. Adjust accordingly if you get no real solution, or you may get the complex solution I. It happens. Reminder that you do have that online quizzes. It's a quadratic check. It doesn't have any of this information, but it has past information that you've been doing. Good luck on the SAT or PSAT tomorrow, if that is what you're taking. And we shall see you next time. I'm going to sign off. Click.
It's all day, the PSATs and SATs?